In this video, we continue with our discussion of molecular structure by discussing heteronuclear diatomic molecules. This diagram compares the energy level structure of H2 with that of hydrogen fluoride, H2 being on the left, hydrogen fluoride being on the right. We talked about H2 in the previous video on homonuclears. So what about hydrogen fluoride? Well, again, let's go back and remember that in our discussion about the construction of molecular orbitals, we said that it's only those atomic orbitals which have similar energies that we will add together. So in this case, from a very simplistic point of view, we find that the 2p orbital on fluorine is closest in energy to the 1s orbital on hydrogen. So we're going to take the 2pc orbital and mix it with the hydrogen 1s orbital to generate two atomic orbitals. We have the bonding orbital, which shows that the 1s orbital hydrogen is added to the 2p orbital on fluorine. It is important to note that in these situations, C1, these coefficients C1 and C2 are not equal to each other as they were in the case associated with the homonuclear diatomics, and we'll have to calculate what those coefficients might be. So we have the bonding orbital and the antibonding orbital as before. What we will also note is because the bonding orbital is closest in energy to the 2pz orbital, that our final solution, the molecular orbital, will resemble the 2pz orbital more closely than it resembles the 1s orbital. The opposite is true for the antibonding orbital, because the antibonding orbital is closest in energy to the hydrogen 1s orbital, that the final molecular orbital will more closely resemble the 1s orbital of hydrogen. Here are the results of calculations for the HF molecule. We won't worry about the details here. They correspond. We'll talk about those in a future video. But we start with our sigma orbitals as linear combinations, as mentioned before, of the 1s orbital on hydrogen and the 2p orbital on the fluorine. When we do the calculations, we will find the energies associated with our two orbitals and the coefficients associated with these two orbitals. Now we will note that the bonding orbital given here has lower energy, negative 19.6 electron volts, which is lower in energy than the energy of the fluorine 2p orbital, which is negative 18.6, so that makes it more stable. The antibonding orbital has an energy of negative 10.3 electron volts, which we will note is higher than the energy of the 1s orbital on hydrogen. So the H11 represents the 1s orbital on hydrogen, and the H22 represents the energy of the fluorine. The bonding orbital is lower in energy than the 2p atomic orbital on fluorine. It's lower in energy than both. That's what makes it a bonding orbital. And the antibonding orbital is higher in energy than both of the atomic orbital energies. Now, if we look at the coefficients here in the case of the bonding orbital, we'll notice that the larger coefficient, 0.84, is on the 2pf orbital. So that means that the bonding orbital, because the coefficient is larger for the 2pf, has a greater character for the 2pf orbital, meaning it resembles the 2p orbital on the fluorine more closely than it resembles the 1s orbital on the hydrogen, which is what we said before. If we look at the antibonding orbital, we'll notice that the dominant term is the 1s orbital on hydrogen with a coefficient of 0.99, and again we'll note that that is higher because the antibonding orbital resembles the 1s orbital on hydrogen more closely. So again, the bonding orbital looks more like the 2p orbital on the fluorine, and the antibonding orbital looks more like the 1s orbital on the hydrogen. Now, if we take a look at the probability densities here and using the numbers on the previous slide, we can estimate the probability of an electron being associated with either the hydrogen or the fluorine in this circumstance in the ground state of the HF molecule. We do that by squaring the coefficient. So for example, in the bonding orbital, we will note that the coefficient corresponding to the hydrogen is 0.34. If we square that, that represents a probability of finding the electron associated with the hydrogen as being 0.12. The coefficient corresponding to C2 is 0.84. Squaring that represents the probability of the electron being associated with the fluorine. And then finally, we have the term here, 2C1C2, which is similar to the interference term. This is the internuclear term. That's 0.17. And so basically what we'll do is we'll take half of that, so that the probability of an electron being associated with the hydrogen is 0.17 divided by 2 plus the 0.12 to give us a probability of 21%. And in the bonding orbital, the probability of the electron being associated with the fluorine, again, is 0.17 divided by 2 plus the 0.71, which gives it 79%. So essentially in HF, there's a 79% probability that the electrons are associated with the fluorine, a 21% probability that it's associated with hydrogen. Should make sense given that fluorine is much more electronegative than hydrogen, and we're going to see that shift in electron density toward the fluorine as a result. Let's look at another heteronuclear example, and this would be carbon monoxide. This is much more straightforward than the case of HF, because carbon and oxygen have very similar energies. They're both in the second row of the periodic table. So when we construct the diagrams, we'll see that we've got a diagram which mixes the 2s orbital on the oxygen with the 2s orbital on the carbon, and we get this particular arrangement of molecular orbitals associated with those linear combinations. Here we see the 2p on the oxygen and the 2p on the carbon. We'll note that the oxygen is lower in energy because it's more electronegative than carbon. If we want to calculate the bond order here, we'll note that we have 2 plus 6 equal 8 bonding electrons and 2 antibonding electrons to give us a total bond order of 3, which again is consistent with our notions about the bonding in carbon monoxide. When we draw Lewis structures, we'll draw carbon monoxide with a triple bond. This ends our very basic discussion of molecular orbital theory as applied to heteronuclear diatomic molecules.